All right, let's talk about something fascinating. There's this ghost lurking inside pretty much every piece of software you use. It's this super elegant idea from way back in the 1930s, and believe it or not, it still shapes how we all code today. We're talking about Lambda Calculus.
Now, if you've ever written any code, you've definitely seen something that looks like this, right? It's what we call an anonymous function. It's just this little snippet of code, doesn't even have a name, and it just does one simple job, like, say, squaring a number. That's the ghost I'm talking about. This small but incredibly powerful idea that haunts our software, showing up in Python, JavaScript, C#, you name it.
So the big question is, where did this powerful idea even come from? It feels so modern, right? Like something cooked up in Silicon Valley. But the real answer, well, it's way older, and honestly, a lot simpler. It doesn't come from software engineering at all. It comes from the world of pure abstract mathematics.
So let's do it. Let's go track down this ghost in the code and find out where it really came from.
Yeah, you heard that right. We're not going back 10 or 20 years. We have to rewind the clock almost a century. We're talking about the 1930s, a time before the digital computers we know and love even existed. The origin of that little lambda you type in your code, it comes from this really deep dive into the very nature of what logic and computation even are.
And that brings us to the person behind it all. A mathematician who is wrestling with one of the most fundamental questions you could possibly ask. He was trying to figure out, what does it even mean to compute something?
His name was Alonzo Church. So think about this. In the 1930s, while the now famous Alan Turing was busy dreaming up his Turing machines, Church was over here tackling the exact same problem, but from a totally different angle. He came up with something called Lambda Calculus. And then, and this is the amazing part, in 1937, Turing himself proved that his machines and Church's calculus were equivalent. They had the exact same computational power. It was like two people on opposite sides of the world digging a tunnel and meeting perfectly in the middle. They'd found the same universal truth about computation from two completely different directions.
Okay, so you've got to be wondering, why the Greek letter lambda? Why a lambda? Well, there's this great little story. Years later, someone asked Church why he picked it, and apparently his entire response came on a postcard that just said, "Eeny, meeny, miny, mo." How great is that? A totally random choice for what turned out to be a profoundly simple and powerful idea.
And honestly, that random choice kind of captures the whole spirit of the thing. See, Church wasn't trying to build some complex programming language. He was doing the opposite. He was on a mission to find the absolute, most basic rock-bottom rules for what computation even means. He wanted to strip everything away and find the purest, simplest ingredients.
Okay, so let's dive into the rules, because this, right here, is the really mind-blowing part. This entire system, a system powerful enough to describe literally any computation you can think of, is built on just three super simple rules. Rule number one, variables. Easy enough. These are just simple placeholders, like x. Rule number two, abstractions. Now that sounds fancy, but all it means is making a function. The best way to think about it is like writing a recipe. The lambda symbol, the lambda, is like saying, okay, here's the recipe. It takes an ingredient, our variable x, and binds it to some instructions. And then rule number three, applications. This is just the part where you actually use the function. It's you in the kitchen taking your recipe and giving it an actual ingredient to cook with.
And that's it. I'm not kidding. That is the entire system. Every complex piece of software, every wild algorithm, in theory, you can break it all down to just those three things. Placeholders, making recipes, and using recipes. That's the whole shebang.
Okay, so you might be thinking, wait a minute, if that's all you have, how on earth can you build anything useful, right? I mean, where are the numbers? Where are concepts like true and false? Well, this is where the true genius of it all really starts to shine through. To get this, you have to kind of flip your brain inside out for a second. In Lambda Calculus, a number isn't, well, a number. It's not a static thing. A number is an action. It's a function. You define a number by what it does, specifically by how many times it tells you to do something. So let's start with 0. What is the number 0 in this system? Simple. It's a function that says, take some action and take something and apply that action to that thing 0 times. In other words, it does absolutely nothing. It just passes the thing right back to you, completely untouched. That's 0. Okay, so if that's 0, what do you think 1 is? Yep, you probably guessed it. The number 1 is a function that says, take an action and a thing and apply the action to the thing exactly 1 time. It's just a simple instruction, do this once.
And right there, you can see the beautiful pattern emerging. The number 2 is just a function that tells you to do something twice. 3 tells you to do it 3 times, and on and on. And what's really wild is that just by using this one core idea, you can build up all of arithmetic. Addition, multiplication, it's all just about combining these action functions in clever ways.
All right, so we've managed to build numbers out of nothing but functions. That's pretty cool. But what about logic? Something as basic as true and false. Can we build that out of functions too? Oh yeah, absolutely.
And the solution here is just so elegant. Think of it like this. True is just a function that you give 2 options to. Let's call them A and B. And it always chooses the first one. It always gives you back A. So what's false? You got it. It's a function that takes the same 2 options, A and B, but it always chooses the second one. It gives you back B. They're just simple choice makers. And from that one tiny idea, a function that can choose, you can build all of Boolean logic. And, or, not. The whole toolkit.
Okay, so this has been a really cool trip back in time, a fascinating piece of mathematical history. But, so what? Why does any of this matter to us, today, sitting in front of our super powerful computers? Why should you care about this nearly 100-year-old idea?
Well, the truth is, its influence is literally everywhere. It's the philosophical foundation for whole families of programming languages like Haskell or Lisp. Remember that anonymous function we looked at right at the start? That's a direct descendant, a lambda. It also gave us a universal model of computation that helps shape the entire field of computer science theory. And even now, deep down inside the compilers that translate our code into ones and zeros, that little ghost is still there, doing its job.
So here's the real takeaway. That little piece of code, that lambda, you type without even thinking about it. It isn't just a feature in your favorite language. It is the echo of one of the most beautiful and simple ideas in the history of human thought. It's this radical idea that maybe, just maybe, the most complex things in the universe can be built from the simple act of making a rule and then using it.
And that leaves us with a final question to chew on. The next time you see some incredibly complex app or a massive software system that runs our world, just take a second and remember Alonzo Church and ask yourself, what if all of that unbelievable complexity is really just a clever, deep, and beautiful arrangement of those 3 simple rules? Something to think about. Thanks for joining me.